Imagine stepping into your favorite world. Enter Genie. What started with a motivation to train generalist agents on infinite scenarios has exciting implications to supplement human creative processes. With a prompt and an initial image, look at how cool these generated playable worlds are. This is what you can do with Genie. Go to the website yourself and play around. Now, I can't help but think about what this could mean for video game development, particularly exploration games or board games, app-based board games behind me with divergent storylines or immersive experiences. Here to talk about this and more is Jake Bruce from Google DeepMind, one of Genie's creators and one of the authors of this paper. Thanks for being here to discuss your paper, Genie. We're happy to have you.
Yeah, thanks for having me.
So before we dive into the specifics of your paper, I read a little bit about your background. It seems like you've been involved in kind of the cool stuff, I'll call it. You did a little bit of game development, robotics. Now Genie. Can you talk to us a little bit about your journey into this space?
Sure, yeah. Yeah, I mean, you got to do what you like so that it doesn't feel like work. So I did a undergrad in computer science. I thought I might go into game development because I've always really loved video games. But I ended up doing robotics because the other thing I really like is automation and interacting with the real world with computers. Um, and so I did a master's degree and a PhD in robotics. And this was about when deep learning was kind of starting to explode and starting to eat all the other fields. And so we started using deep learning at the end of my PhD. And then I ended up joining DeepMind robotics group as well. Since then, I've done a lot of mostly reinforcement learning in simulated robotics domains. But the thing that's probably best known from my portfolio is a work called Gato. The paper is called A Generalist Agent. And the idea was that we would use a transformer, which has this very general structure, like you just have a token stream and then you can learn to predict the next token. And we use that to condense many, many different behaviors into one network. And I think that's when I really started to realize the power of just scale, model scale, data scale. You can kind of fit any function if you have enough data and compute. So that is kind of a spiritual precursor to Genie in a way, because the hope here is that we can fit the dynamics of interactive environments with big data and big compute.
Yeah, and elaborate a little bit more on that, on the motivation behind Genie.
Yeah, so I used to be in the robotics group, but I've joined the open-endedness team at DeepMind. And what that means is that we want to be able to develop algorithms that can kind of continue to improve forever. And so, the science fiction notion of superintelligence is that it can kind of go off and explore new things and learn new things and convey that back to the people who designed it. And one of the big challenges with training a reinforcement learning agent forever, is that you'll run out of things to do. You'll run out of tasks to solve. You'll run out of new behaviors to learn. And so the motivation for Genie originally is that rather than try to onboard every single video game and RL environment into one code base and then be able to train an agent on them all, which would be an amazing set of experiences for the agent to learn from. But even then, it's finite. What we thought is, what if we can train a generative model on these instead, such that it can continue to generate diverse, interesting tasks and environments forever? And that's the original motivation. So we started with some reinforcement learning environments like Atari, and CoinRun is in the Genie paper. And yeah, the hope is that we can eventually train agents on these. That's kind of future work, but so far we have some preliminary examples in the paper where it seems to work well.
Yeah, and this is something I'm interested in just in reading the paper, talking to other people. It seems like there might be a little bit of a divide. So potentially this could be used to train generalist agents. That's kind of sci-fi notion of AI. What do you say to people that are scared of that technology or that see AI as do the monotony, take that workload from us, assist us, but kind of leave the creative stuff to us.
Yeah, I totally sympathize with that viewpoint, actually. So I think that as someone who really loves video games, if you were to, for example, generate video games from scratch with deep learning, I think that you would have a big challenge making them engaging in the way that a human crafted game is, right? There's kind of a soul of creativity that you really want for a high quality gaming experience. So that makes a lot of sense to me. I think that effectively the issue, though, is that there's this phenomenon or idea called Moravec's paradox. And the TLDR of Moravec's paradox is that the things you think are easy are hard, and the things you think are hard are easy. So, an example of that is that playing chess is like a really difficult intellectual pursuit for a human, but it's one of the first big splashes that we kind of solved with AI.
Mm.
Whereas picking up a spoon with a robot is easy for humans, but it's very, very hard to get right in a robust way across a lot of environments and so on. So I think that in order to kind of master the easy tasks for us, you need a lot of behavior data and a lot of learning opportunities for the agents. And so simulating environments for them, I think, is a really important way to learn those behaviors. And sometimes that ends up looking like simulating kind of creative, artistic things that humans would create. But I think at least with Genie, the hope is that we're not trying to automate away any kind of human creativity, but just to provide as broad as possible a set of experiences for the agent to learn from.
That makes sense to me. You alluded a little bit to the problem space. Walk us through an overview of the paper. Let's start with the design. It's a three component design. You also train it differently than other world models.
Hmm.
Tell us a little bit about that.
Sure, yeah. So the fundamental goal of Genie is that we should be able to train on any data we have access to. And the difficulty with that is that in order to produce something like a reinforcement learning environment, there's two important things, and those show up as two of the components in our model. One is the kind of environment state, and then the other is the environment dynamics, which is usually controlled via a variable called an action. So you have some state, your agent will take an action, and then you observe the new state that kind of incorporates the change that was created by that action. So we have a dynamics model in our kind of overall structure of the model that accounts for kind of creating the next state. But then the difficulty is the actions, because no matter how much kind of data of interactive trajectories experiences you have on the internet, very, very few of them come with strong action labels. So precise variables that tell the machine learning system how, like, what is the causal intervention that caused the particular trajectory that you see. So for a video game, the actions take a very straightforward form. You have controls from the human player who is sitting down and playing the game. That can take the form of button presses on a joystick or keyboard and mouse controls. But those just aren't available for most of the data that's recorded in the world. Take robotics as a different kind of example where almost everyone who records a robotics data set does record the actions because they have them available, and it's usually explicitly for some kind of robotics machine learning purpose. So, they realize that the actions are an important piece of information to gather. But if you want to scale to as many videos of interesting behavior as you possibly can, then you can't rely on actions being there. So that's the second important component of our model, is what we call this latent action model. What we want to do is infer a kind of latent variable that captures the essence of the causal intervention that the human was doing when they were playing the game. And ideally, this behaves a lot like an action. So I would say ultimately there are a lot of video generation papers out there. There's a lot of world model papers out there. But our approach is unique, I think, in the world model space because we're explicitly not requiring the actions. We're trying to infer them from
Right.
data.
And what experiments did you use or did you do to evaluate the model?
Oh, yeah. So it's evaluation of generative models is very hard. So I'll start with that. So the reason that's hard is because you're not necessarily training the model to produce a particular outcome, you're training it to sample from the distribution of all outcomes. So that means that, let's say you're training an image generation model. If I type in hamster wearing a spacesuit, there's a lot of possible images that would be really great instantiations of that prompt. And so instead, you have to kind of measure some degree of like, how well does this fit the distribution, rather than did it produce exactly the right output. So our evaluations in Genie take a couple of forms. There's this metric called Frechet inception distance. So this is basically a measure of how similar two distributions are. And so if you generate a bunch of examples, videos or images, you can kind of measure how similar is the distribution of real data to your generated data. So that's a quantitative metric we use. Another thing that we're very interested in is measuring the quality of the latent actions, because, of course, they're totally unsupervised. There's no real strong reason why you would expect it to kind of nail the semantics of the particular environments you're training on straight out of the box. So we have a couple ways to get at this. Most of them involve something like you have a reference trajectory that's from your data set. It's like a video of someone playing a game or an agent running through a level in an environment. And then you start with the initial image from that trajectory, and then you roll out the model on the series of latent actions that you've inferred from the trajectory. So you infer the latent action sequence, you run the model with those latent actions, and then you want to measure how much the trajectories diverge.
Mm-hmm.
So if you assume the latent actions are kind of really nailing the most important semantics of the control of this environment, then you would expect that the real trajectory and the one that you generate end up being pretty similar. And so for that, we use typical image distance metrics like PSNR. But the idea is that you should see when you use the right action sequence, it should be very close to the reference. And if you use a different action sequence, you should get something different than the reference trajectory. That's one of the ways we measure this.
You call out too in the paper video fidelity, that's what you're referring to here, and controllability, right?
Yes.
You were just talking about the controllability part. Can you elaborate more on that?
The controllability, to be frank, it's a hard thing to measure. So I'm not sure we've even nailed that today. But that's what we're measuring here. So we report the PSNR diff, which is our way of saying how well does the generated trajectory match the reference when you have the real actions, and how much better is it than if you used a different action sequence, usually a uniform random sequence. So it gets at controllability a little bit, because you're saying, okay, at least when I use the right actions, it's much, much closer to the reference trajectory than when I use some other action sequence. Now, there's something more to say about that, which is that controllability, so ideally, and just implied by the term controllability, you might want it also to respect the semantics of human control. So that's a very, very hard thing to measure, because in a simple environment, you might know in advance that the actions are move left, right, up, down, whatever, simple, semantically meaningful actions. And then you would want the latent actions to kind of be isomorphic to that. So one of the latent actions, you don't know which one in advance because it's unsupervised. They're learned from scratch. But hopefully, one of the latent actions that come out of the model controls one of those real semantic controls. And that is very hard to measure a priori, but qualitatively, we find that they do tend to work pretty well. So we tend to find that there's reliably an action for moving right, an action for moving left. In this work, we trained the model primarily on 2D platformer games. Nice thing about that is that while there's still many of them, there's thousands and thousands of 2D platformers that have been made, they have relatively consistent semantics. So you can usually move left, move right, jump. Often there's an attack animation of some kind. And we find that these latent actions, just qualitatively speaking, we don't have numbers to back this up, but there are examples in the paper and on the website. Qualitatively speaking, you tend to reliably find a move right action and a move left action and jump and so on. And those actions tend to be consistent between games. So that's another aspect of controllability that's a little hard to quantify. But the hope should be that if you instantiate an environment that, it's an underground world with a green character, and then you instantiate a cloud world with a blue character, you would hope that the actions still do the same thing in both of these environments. And we find that they do. And quite frankly, we were surprised by this. So it's just one of these emergent niceness that you sometimes get with deep learning. Like it just learned the thing you wanted without having to work super hard at it, which was very good.
Yeah. So this is unsupervised. Like once you press go, it's unsupervised. But Genie is trained on, and I'm gonna keep it simple with the acronym VQVAE,
Yes.
um, which the based objective. Tell me how important that is because of the latent action design, right?
Sure. Okay, yeah. So that you mentioned earlier that Genie has kind of three components. I only really focused on two, but that would be the third component.
Okay.
And we refer to that as the tokenizer. I suspect, because we've done a lot of investigations of like variants on this and different components, this is primarily just a practical decision to get the model to work. And so the reason we have a tokenizer is that our dynamics model is based on mask-GIT, that's masked generative image transformer. And the fundamental operation of mask-GIT is a discrete sampling based thing. So you produce the logits for a categorical distribution over the every token in the image, and then you gradually sample more and more of them and fill out the image. It's a nice cost saving trick for generating images very rapidly as opposed to doing every token at once. But the fact that it is sampling discrete values means that your data needs to be discrete, just like the tokens in a transformer for language, for example. And images are not discrete. It's a continuous valued tensor. And so the VQVAE thing is just a necessary pairing for the mask-GIT generative model. If you took a different generative approach, let's say diffusion, right? So you denoise in continuous space to generate the next image, then you wouldn't need a tokenizer. So you wouldn't see this VQVAE.
Okay. Now, am I misunderstanding something? Because later in the paper, I think in the ablation studies section, you talk about the choice that you made of using an original image in pixels versus the tokenized image. And I think you went you opted for the pixels, right? The original image,
Yeah.
although you did studies with the tokenized image. Explain to me why I'm confused.
Yes, got it. That is confusing, and it's a detail I wish we didn't have to use. It's just one of those things where you try a bunch of variants, and one of the not so nice ones ends up working the best. So, yeah, the confusion here is that our latent action model, which is the thing that infers the control unsupervised, that model has its own entire dynamics model inside of it in order to provide signal for those latent actions. Because the way we learn them is that we want to encode the future in a very heavily bottlenecked variable, and that's a discrete vector quantized variable. Tends to take 8 values or so, so it's like extremely bottlenecked. And you use that latent action to predict the next state. And that's all just the auxiliary loss for the latent action model. And so the confusion is that, of course, that dynamics model is not the one we actually use to show images to the user. That's just the one we use to get the signal for the latent actions. And that dynamics model tends to work best in pixel space. So our actual
Got it.
heavy duty generations are happening in tokenized.
Tokenized.
Yeah. And then the ablation you're referencing is the fact that we tried to train the model, the latent action model, using the tokenized space instead, and it just didn't tend to work as well. So the actions weren't as consistent, quantitative metrics weren't as good. And you could speculate about why that might be. So the VQVAE that produced the tokenized codes, this is an autoencoder. So it takes the image, it represents it as a series of discrete tokens, and then it tries to recreate the image from that. So the idea is that if you are very good at doing that, then you must have captured everything you need in the tokens. And so they might be a good basis on which to do further learning, like dynamics learning, for example. But you might speculate that while that's good for reconstructing images and videos, it doesn't necessarily carry the kind of control information. So perhaps it's too easy to infer where the character will be next given its momentum. And so the model doesn't waste a lot of capacity actually representing that in the codes, for example. Um,
Okay.
we don't have rock solid evidence that this is the case, but it's one of the reasons you might expect something like this to happen.
So you already mentioned you trained on 2D games, but reading the paper or if you go to the website, you can see a lot of cool stuff. It's generalizes to 3D environments, sketches, real world photos, like a lot of really, really cool stuff. So, and one of the emergent capabilities that you mentioned in the paper was emulating parallax. So, foreground moves faster than the background or middle ground. Was that an unexpected quality?
I think it's one of these things where if the model's doing its job well, you need it. So, like a lot of 2D platformers have parallax. So, it's a very efficient way. Historically, in early gaming, it was a way to get the illusion of depth without while only having
Hmm.
just a few layers. Nowadays, most of these games have full 3D rendered backgrounds, but they also have this property, right? So, the mountain in the distance will be there for many, many screens, even as you're just scrolling to the left while everything else changes, right? So if the model
Right.
is good at modeling this kind of data, then you should see parallax emerge. And I think we just like to put it in there because it's just a very striking kind of property that these games have, and it's clear that the model really knows about it. And the cool thing is that you're just providing it a single image. So the image doesn't really have encoded in the pixels
Right. It's not.
anymore. There's nothing about the depth, but
Yeah.
it just turns out that the model has a pretty good sense of like, oh, that thing looks like its background. And there's also several levels of parallax, right? So that thing in the very far distance looks like it's very far away because it's a mountain and it's close to the sky or whatever. Whereas this platform that's in between the two is not foreground. It looks like it's too far away to be foreground, um, but it's still not the background either. So it knows to move that more slowly than the foreground. Um, yeah, it's a nice little kind of case study on is the model learning the right kind of dynamics. Um,
Right.
you also mentioned the generalization, which to hand drawn sketches and to
Yeah.
real world photos and stuff. Yeah, I was blown away when we first started trying that. It's one of these things where I'm sure there's a lot of papers out there that would have found really cool things their model can do if they just tried weird stuff. Because why do you put a photo of a pizza into Genie? Like it doesn't make sense. But it's just the case that when you train on a large amount of data that has somewhat consistent dynamics, you can get the model to do something sensible. There's still improvements to be made, but it'll do something sensible on these out of distribution things. Now, I'll tell you my very favorite example of all of those. It's maybe not the most impressive one, but one of our advisors, one of their kids, drew a picture. This was just, their children drawing pictures. But this particular picture had, as part of the picture, it had drawn a picture frame. So the
Mhm.
outside had a border of a picture frame. And the absolutely amazing thing is that the model left the picture frame intact and moved only the things that were inside the frame, which is like,
Really?
that's yeah, and I think we have that example somewhere on the website because it's so good. But that's great, right? That's a little bit like a lot of video games have some kind of decorative filigree around the edges. Many of them have UI elements that stay in place even when your character is moving around. And
Hmm.
the fact that the model picks up on that is a really, really great signal.
Yeah, that's amazing. So you and your team, you're just like, oh, let's try. What was first? Did you try the real photo? I'm assuming 3D games was first. It's the obvious jump from 2D games. You.
That's a good question. So, what our okay, the kind of simple chronology is that early on we were testing on kind of in distribution samples. So we would have a validation set, but it's all just screenshots from video games that were in the training data. And then we have out of distribution examples. So this was where we thought our target would be is that
Okay.
when I get Google Imagen to generate an image for me, some text to image model, I should be able to prompt it with like, okay, this is a game about an archaeologist exploring a tomb, and it will give you a plausible screenshot from a game like that, and then we can put that into our model and then play the game. So it's a game that never existed, but it came from a generative model, and we can then play it. So that was our goal, because what that allows us to do is like Genie takes care of the dynamics of the environment, but we don't actually take any responsibility for generating the initial frame. So like we just kind of assume that's an input that's provided. And the motivation for that is basically that image generation models are really good. You know, we don't necessarily need to like reinvent the wheel there. We can just provide the dynamics. But of course, an image is an image in terms of like NumPy tensor shapes and so on, right? So like we had all sorts of images that we put in. I think that after the generated images, I think we probably put some of the real world photos of our team lead's dog, so that those there's a gradient of like quality, right? Like when you're doing in distribution stuff, it feels basically like playing that game, but then generated screenshots don't work quite as well. And then you put in a photo of a dog, and like miraculously you can move the dog around,
Yeah.
but it's not like running and jumping or whatever. It's just you're just moving it, but still pretty amazing. And then I forget why we originally put in some of the hand drawn stuff, but I think the idea was just kind of explore. We're generally a very exploratory project, so we have this weekly kind of session that we call the Genie Bottle Challenge, and our idea is that you should give the model a screenshot of a game with a genie and a genie bottle, otherwise known as a lamp, and you should be able to jump around the platforms and get the bottle. Right. So early
Mhm.
on, that was impossible because the model was too bad. But near this time last year, which is about when the paper results were coming in, we were reliably able to jump around and get that bottle. And then I think the idea was, what if we could hand draw like screenshots? If you could
Right.
just sketch out what you want your game to look like, and then the model could animate it. And yeah, it kind of works better than you'd expect. No, I'm not looking to go publish something on the App Store because it's not that fun to play these yet, but like it works technically.
That's really cool. My English teacher, former English teacher brain going, well, I'm going to skip a little bit ahead. So you end the paper, kind of just some allusions to a potential future, specifically children imagining worlds to step into, or using Genie in the gaming industry for playable world development. I'm just reading. We're not ready to publish an app in the App Store, but how close are we to that kind of future?
Yeah, I probably can't make any predictions because you never know what amazing developments are going to happen any moment. But I would say, like in the long term future, it would surprise me if there weren't some kind of video game interactive experiences of some kind that were entirely generated, completely end to end neural network controlled. Um, it's a challenge though to figure out how you might make that fun, make it an interesting experience, because um, we're already seeing suboptimal the prompting interface is to these models. So the fact that a prompt engineer is an actual role that people can take,
Role, yeah.
that seems like evidence that the prompt is not it's hard, it's subtle, it's hard to get it right. So how do you prompt something to make a fun game to play? That stuff seems really hard. So I would say, yeah, can't make any actual predictions, but it's going to be a while before we see these
Yeah.
things really taking off. But our team, we enjoy playing with it as as researchers looking at the outputs of their model. It's still kind of fun to mess with,
Yeah.
and so I think there's something there, but it'll be a while.
Yeah, I'm just imagining a classroom, the accessibility and the engagement that you could create. That'd be really cool if you could get the prompts good enough that high school students could reliably turn their own work into something like that. That would be really awesome.
Oh yeah,
Um,
I have no doubt that will be something that will happen. Probably not in the next year or two.
so tell me that now that's just making me think just with even with GPT and all of this stuff, out of curiosity. Do you think this model or something like this in the future and enables imagination or replaces it and limits it?
Yeah, so because I really like video games and I've followed a lot of game developers, there is there's something special to the kind of unique authorial vision that a game developer has. Like some games are just true works of art, not just in the visuals, but like the game design. And we're certainly not at a stage where we can expect neural networks to do this, right? So, you know, language models are getting better every day. I think people aren't reliably generating things that are like mind-blowingly good writing.
Hmm.
So that's still to come in the future. But I think even once you get to a stage where these models are producing a game just as good as a game that could have existed, I always struggle with computer generated content because I think there are some games that use it very skillfully, but it's easy to use it just unwisely. So it's this concept of like the procedurally generated content in the game is a mile wide but an inch deep. So you will continue to experience technically new things, but after the first few minutes, you get a feel for what the distribution of things is, and so even though you couldn't have predicted it, it's not that interesting. And I think
Right.
that AI generated content is going to be kind of like this for a long time until we really crack like what is it that really how do you get really skillful use of computer generated stuff. And then in the even longer term, it's hard to get around the fact that it's just something special about a fellow human like you. The person who made this was just like you. They had an experience like you, and they just sat down at a computer and learned how to do art and programming. And so you could have done that too.
Yeah.
That real connection to the author of the work is important. So, yeah, just as a researcher, it's super fascinating to see what bounds we can push on computer generated content. Image generation today is incredible. But there wasn't a human involved, so it's not the same. And I think if you're a company that I think we're seeing a lot of backlash these days about like AI generated art being used in products, and fans aren't always happy with it, and other companies aren't happy with it, and artists aren't happy with it. So it's just a situation where there's still something important about having the human in the loop. Now in the classroom, I mean, like I think we'll see how that goes, right?
All right, so let's go back to your paper. Most of the paper is obviously telling us, the design and the training and all of that, and then a lot of the examples are these images. But you do talk about robotics, and now I know that you have a background in robotics. So can you elaborate a little bit on the implications, as you see them anyway, of Genie in that space?
Yeah, totally. So, at a very high level, simulations are very important for robotics. So, the difference between an Atari agent and a robot trying to pick stuff up on a table is that, like, you can run Atari at, I don't know, 10,000 frames a second or something. You can generate so much data, and it's very, very cheap and parallelizable. But robot data is expensive. It runs at the frame rate of the real world, and there's nothing you can do about that. And so simulations in robotics are very important. And on top of that, simulating robotics is very hard. In particular, little things like contact dynamics are really difficult, right? Getting the physics right of how your fingers interact with the object you're trying to manipulate. That stuff is just a nightmare to get right and very expensive in terms of like computer CPU cost if you do attempt to get it right. Um,
This
so
is sorry. This is like grip strength, kind of that kind of thing, or
well, like so take this cup like this cup is actually tapered, but if you imagine that it wasn't, a human could still hold it with two fingers.
okay.
But why is that, right? If there's no force acting upward, what is holding the cup there? Well, it's because there's friction between your fingers and the cup that produces a force that resists gravity. But the pads on a human's fingers are very sophisticated. They're soft,
Right.
but they also are full of touch sensors. So if you reach into your bag and root around for your keys, you can find them without looking in the bag at all, right? Just with your physical interactions. Um, and that's an enormous amount of data, and it's very hard to get those
Mm,
interactions simulated accurately. So it's things like that,
okay.
and even beyond just contact dynamics, although that's a very common um, issue with simulations. Think about things like fluids. So like any I don't know when, but sometime in the next decade, I'm sure you're going to be marketed a robot that can make cereal for you in your kitchen or something. Simulating a bowl of cereal, going back to Moravec's paradox, simulating a bowl of cereal is way harder than playing a game of chess, right? It seems very simple, but it's very, very complicated to get fluids right. So that's why you want high quality simulations, because they're hard.
Yeah. That's a tough one for me to get right. Like, I prefer a specific amount of milk. I don't want soggy cereal. I want a little bit of crunch, you know?
Yeah, I was just talking about the milk sloshing around in the bowl, but if you're trying to model human preferences on Rice Krispie crunchiness, that's hard.
Yeah. So, what are the implications? Genie could be used how?
Right. So, because simulations are both important and very difficult to get right, you might naturally think, could you learn the simulator? There's a lot of good robotics work in this space. So, the whole area of model predictive control is kind of the idea that you have a simulator for your robot and use it to plan what to do. So, you can kind of figure out what will happen before you actually go out and try it. And as long as you have a simulator, then that is a viable control strategy. And if you don't have a simulator, then you might have to learn one from your own experience or from massive data sets or whatever. So
Okay.
Genie is a learned simulator. So the idea was like, okay, how this works on 2D platformers, how well does it work on robotics?
Right.
And we were kind of always investigating them in parallel because it's always nice to know that it works on other domains. If it's a good idea, it shouldn't just work on 2D platformers, but it should work elsewhere. And so it's kind of a proof of concept in terms of, as you see, we don't dedicate a lot of space on it in the paper, but we were happy with the results. And the idea is just that if you use this robotics data set, these particular data sets we used were all um, kind of egocentric views of a robot arm interacting with things. So pulling out drawers, picking up objects and moving them, that kind of stuff. So you can see your own arm moving in the frame, you know. And so the things that are under your control are your own arm, its position, and the objects that it interacts with. And ideally, the latent actions that we learn, you know, they work well in 2D platformers. They should also control and consistently control the movement of the arm and the objects it interacts with. And we find that it works pretty well. There's a caveat here, which is that I mentioned this earlier actually. Every single robotics data set basically has the actions already, right? So
Right.
why would you try to learn a latent action space? So in that sense, robotics is a little bit, while it's a cool use case for the model, it's an awkward one to sell because it's maybe one of the domains that you least need the core contribution
Mhm.
of our paper. That said, though, we don't have any evidence for this, but I could imagine all sorts of interesting use cases that are something like, you know, you don't just have one robot, you have 100 different robots with different kind of configurations. And this one has wheels and this one has legs and this one has a parallel gripper and another one has like a humanoid hand. There's a suction cup gripper that's very popular in industrial robotics.
Mhm.
So like how are you going to learn a control space, or how is your model going to use the control spaces for all these 100 different robots? Well, then maybe a latent action space starts to make sense again in that setting. So,
Okay.
you know, we don't know exactly what kind of pneumatic pressure we're applying to the suction cup, but we know that the general movement we're doing is to move forward and touch the object and then somehow pick it up, right? And that's the kind of thing that might be encoded by the latent actions. In the paper, we have exactly this setting. So Genie has these unsupervised actions. So how do you actually use them to do anything when you make contact with the real world or the real environment that you were learning to
Mhm.
model with Genie? And for that, we used the ProcGen environments, which are very popular benchmark environments for reinforcement learning. And the nice thing about ProcGen, there's a couple nice things. One, they're relatively simple, so they would be fun for a human to play for a few minutes, but they're not much more complicated than that. But then they're also procedurally generated, so they're kind of infinite variety within the domain in terms of variable background textures and like level layouts and so on. But then the reason that they're very useful for evaluating the model in this setting is that you can record the actions. So you can take reinforcement learning agent trajectories that have ground truth actions. And then what you can do is if you train the Genie model totally unsupervised on these reinforcement learning trajectories, you can then learn a very lightweight mapping between the latent actions and the real actions with very little data. So I think I
Hmm.
have to look at the paper for this, but it's like less than 100 time steps of experience. So that's not like 100
Right.
levels or 100 sessions. It's like literally 100 button presses, and you already are approximating kind of the performance of the expert with that little amount of mapping from your latent actions to your real ones. So the robot situation would be a much more interesting and realistic version of that same problem.
Right. Cool. What are the limitations of Genie that require future work?
Yeah, totally. Yeah, I mean, so we're all still working on this. We're all very excited, and there's so much more to do. But some of the things in particular, not sure how many of these we called out explicitly in the paper, but one is the inference time. So our largest model in the paper was, I think, 11 billion parameters. That's a pretty hefty model to be stepping at real time, you know. So I think in practice, without having optimized it at all, because we weren't really focusing on user level experience, but without having optimized it, we were getting about 1 frame a second. So that's relatively slow compared to the underlying data, which was 10 frames a second. And that is a matter of maybe new inference time kind of architecture optimizations. So take something like Mamba or state space model architectures. Those have this nice property about of being basically constant time and relatively fast. And I guess so. The constant time thing doesn't imply speed, but it does imply you don't lose speed as time goes on, right? But with transformers, the longer the context, the more compute you have to bring to bear, and the slower it is. So I'd say the speed is slow, and it gets slower as you play because the context increases. And you can truncate the context, but then of course you kind of forget things earlier. So that's another useful limitation to mention is that in the model, in the paper, we were training on 16 frames of context, which is a nice power of two, and it's feasible to train on because it fits in memory, and it's not too expensive to compute the attention. Um, but at 10 frames a second, that's 1.6 seconds of gameplay. So it's really not a lot of context to leverage for like, long horizon experiences where you explore a whole castle or something and then you can come back to the same place and it still looks that way. We have a lot of kind of qualitative examples where you go off to the right and then come back and it of course looks completely different than it was
Changes.
when
Yeah.
you were there. Yeah. And that's kind of a fun little quirk, but it is a limitation for sure if you want to extend this to meaningful long horizon experiences. So I would say, yeah, speed, long horizon consistency still requires work. These two things are kind of, I don't want to say engineering problems, but there's a lot of engineering approaches that you could take to mitigate them. So some of these modern language models have 10 million tokens of context, right? So that wouldn't be 10 million frames because each of our frames is many tokens, but it might be 1,000 frames or 10,000 frames. So with some really good engineering, I bet we could push that up, or someone else could. It's totally feasible. There are some more fundamental things that are very hard. So image quality is something that you can address. So we find that due to the autoencoder and then the kind of drift in quality, the reduction in quality you get as time goes on, we find that like the initial image is very crisp, but then kind of loses some detail as you go.
Hmm.
And then if you play long enough, it'll become just nothing but blur. This is a fundamental issue with model based, any kind of world model things. So in robotics, all of the model based architectures suffer from this problem, basically, which is it's accumulation of errors that kind of diverges you off the manifold of real possible trajectories. And it's very hard to fix that. And I will say language models, for example, aren't immune to this either. So if the problem is every step of sampling that you do, if you make even some small error, you don't ever get to go back and rewrite your history. So you just have to work with that error, right? And if the image got a bit blurry, well, you're in a video that's getting blurry now, so it's going to get more blurry. Um, and so that's one thing that's very hard about our setting, being purely autoregressive. Whereas if you imagine many video generation approaches these days they're done in a batch, so they spend all of their compute refining the whole video, able to change the past and the future as they go, and then you only need to see the output, and then it's like a static fixed artifact. And you can watch it as many times as you want, but it's just one chunk of data.
Right.
We don't have that luxury. We have to actually get every decision right along the way as we go, and so the autoregressive nature of it makes it harder. Um, and that solving that, I think, will require some really interesting memory innovations, some kind of way to anchor the quality so that you don't diverge arbitrarily far. You should at least um, diverge no more than some tolerated amount.
Right.
And then would say the last thing, there's just so many interesting things to work on. So our limitations list is pretty long, but I would say that control is not yet perfect. So the one thing that I struggle with is non-player characters. So, and more generally, like environment dynamics that aren't under the control of the player. In practice, we see that like simple characters, like take a typical platform game, will have like some enemy, like people moving around, and you have to like jump over them and avoid them or whatever. As long as their behavior is very simple, like easy to predict, then we find that they don't dilute the quality of the actions. So like the actions aren't trying to dedicate their capacity to control these little creatures because they're predictable. So it's not going to waste its own modeling capacity on that. It's going to spend it on the difficult things to predict, which are like the human controls, because the human can do anything at any time. But not all things in all games are like that. So if you have any procedurally generated content, like let's say I move to the right in the game by pressing the right arrow, my character will move to the right, but something will be revealed off screen, a platform or some more of the background or whatever. And if this is a truly novel game, those things are just not predictable in any way. And so they either have to be encoded by the latent action, which would be bad, right? You don't necessarily want the actions to control the environment generation, or they have to be ideally like kind of a function of the random seed, like just however you randomly initialize it, that should kind of determine how these environment things get generated. Um, and you have no control over it, but you at least know you've factored it out from the control of that the human is doing. But this is one of these like fundamentally thorny causality problems, because if you don't have any labeled actions, those two are kind of indistinguishable, right? Like they're both unpredictable things. And so, how do you encourage the model to learn this kind of unpredictable thing and not that other kind? So,
Right.
that's a very hard problem.
Yeah. I can imagine that. I'm just imagining some like Baldur's Gate or like some of these games that have they're world exploration games. You're supposed to discover things that aren't readily visible or predictable. The characters make weird the non-playable characters completely come out of left field sometimes.
Yeah,
Uh,
and you want to be surprised by those things and to not
yeah.
have them be like covertly controlled by your own actions by accident in a way that's
Hmm.
inscrutable. Oh,
Yeah.
if I go left before I jump, then I get a platform, and if I go right before I jump, then I get a pit. Like
Right.
you definitely don't want that.
Right. Right. Yeah. Okay. That makes sense to me. So obviously you curated the data sets for this training, but I am curious because it's unsupervised. So I'm
Mhm.
curious about a model like this generating unwanted content or even harmful content, I guess. Is that a legitimate worry or what are your thoughts on that?
Yeah, I mean, in general, it's a very legitimate worry when you're training on kind of data from the wild like this. I would say in our case, we feel pretty confident in it for two reasons. One is the curation. So we haven't observed every video ourselves, but the way we did it is we labeled something like 10,000 videos for our quality classifier. And then we trained a model to predict our quality scores, and then used that to filter down to just the 10% that is the best data in the data set. So that allowed us to explicitly label stuff that we didn't want as undesirable. So, we can't guarantee everything in the data set is that top tier of quality, but we almost never see anything objectionable when we actually look at the data. So we're pretty confident about that. But then the second thing, which I think is really even more important for our use case, is that we simply don't generate the initial frame. So if something unsafe or bad were to happen, it would have to happen as a result of either the initial frame being bad to begin with, or the model kind of getting to something bad from the initial. And I think the combination of those two kind of safeguards makes me feel pretty good about this. But that said, like if at some hypothetical future, if we ever were to make some sort of product with this, like that, yeah, that would be hugely important, right? Obviously,
Right.
yeah, these models, by the very nature of their breadth and power, they have the ability to do things you don't want them to do, and so that a lot of mitigation needs to go into that. And
Right.
we happen to not have that problem at the moment.
Comes down to that first frame and whatever the user input is.
Yeah,
Yeah. Okay. Given the amount of data, and which is a lot, and resources, which is a lot, required to train these types of models, how can we hope to make this kind of technology more accessible so that more people can get in on this and work in a meaningful way toward solving any of the limitations that you just suggested?
yeah, totally. So we have a section in our paper about reproducing this at kind of reasonable scale. So the case study that we outline will fit on a standard home GPU, a single machine GPU setup, and you can successfully train coin run model. So that's one of the ProcGen environments. A coin run model on those resources in, I forget what the timeline is, but it's like a few days or a week or something, pretty reasonable. And already in coin run, you start to see some of the cool things that the model can do and some of the limitations, right? You'll start to already be able to explore things about action consistency and the importance of the data diversity, for example. Like if you use biased trajectories, like if they go right more than they go left, then that will introduce issues that you can study in those domains. So that would be the first thing. And I should also say there, like several research groups have actually reproduced this in that way. I think there's a ICML poster, for example, that they presented some results where they reproduced this. And there's also this, unfortunately, I'm going to forget the name of it, but there's this kind of open world models competition thing where a Genie based architecture that was not done by us is one of the competitive models there. At some point, it was the top of the leaderboard, but I don't know the state of it now. So there's that. And so basically, that's by virtue of kind of scaling the model down and scaling the data complexity down. Now, our goal in the paper was to kind of tackle something that's at the limit of even what we can do. So we wanted to make sure it's not the upper bound by any means, but we wanted to make sure that we got as good of a result as we possibly could. And so we were training on as much data as we could with as much compute as we could.
Right.
In order to tackle that kind of regime, it's the same kind of situation with language models. I think like there will be architectural improvements. There will be kind of distillation approaches, for example, that can get a big model's quality in a small model, which you see with something like Gemma, for example. That's a small model that's achieving really quite good language model performance. And you tend to see this happen in machine learning where you get some really nice proof of concept at large scale and then people kind of squash it down by work on optimizing various things and improving architectures and data mixes, for example. And then, of course, there's just time. So even if none of those improvements were possible, the hardware will get us to a point where you could train Genie in an afternoon, like, and we'll of course be looking back on it being like, I can't believe we spent a month training this thing. But no one wants to wait a decade or whatever for that to happen. But it's optimistic in the sense of future applications of this kind of thing will be running on much better hardware. So it'll be
Right.
feasible to run them at home, for example.
Okay. So you said you're still working, you and the team, your team are still working on this. But yeah, what's next for you? Only this, or can you share what's next with this? What's coming up that we have to look forward to?
Yeah, I'm super excited about the kinds of results we're getting these days because, like I mentioned, these results were from a year ago. So we're really, really happy with how much progress we've made. I probably can't give any any real tangible details, unfortunately, but it's the kind of thing you'd expect. So we're broadening the scope of things. We're training larger models. We're improving our generative modeling and improving our
Mhm.
action control. And yeah, it's getting better every day. But I would say, like even now, I'm super thrilled with the outputs we're getting. But it's like you would still wouldn't want to play this for more than like a few minutes or something. So yeah, there's a long way to go before we get super killer demonstrations or products
Right,
from this kind of technology. We're very much a
right.
research project.
Awesome. Well, we'll have to stay tuned for future releases, I guess. But thank you, Jake, for your time. I really appreciate you joining us and really excited about whatever comes out next.
Absolutely. Thanks for having me. It was a great conversation.